Good evening, everybody. I'll be presenting my major project for my pre-grad course of DSA, and I'm studying at SPIT, and this is my second year. So the title of my project is Sales Prediction Using Multiple Linear Regression. The purpose of this project is to predict sales using an advertising expenditure on three different channels: TV, radio, and newspaper. I'll explain the project as a machine learning workflow. So first, before starting the code, let's understand what the problem actually is. It is a machine learning problem because the data supervised machine learning problem because the data set contains the input values as well as the correct output value. And since the sales is a continuous numerical value, regression is used here, and it is called multiple linear regression because we use multiple input variables to predict one target variable. The general equation is predicted sales equals the intercept plus the TV coefficient multiplied TV expenditure plus radio coefficient multiplied by radio expenditure plus newspaper coefficient multiplied by newspaper expenditure. The intercept and coefficients are not manually selected, the model learns them from the data. So first I'll require the install libraries, and I've already installed them. Next, I'll import the libraries. So pandas is imported as PD, numpy as NP. The pandas, it provides a data frame which stores the data set in rows and columns, similar to a spreadsheet. Numpy is used for numerical operations. Like it is used to calculate the square root for RMSE value. Seaborn and Matplotlib are used to create plots, visualization. Linear regression is the machine learning algorithm used to train the model, and train test split separates the data from used for learning from the data for final evaluation. R square and mean square error are used to measure model performance. Next step is loading the dataset, and I load the advertising dataset using this cell. I've already loaded the dataset here. The head method displays the first 5 rows. So I can easily check if the all the columns are loaded in properly, which they have. Next, I inspect the data. I check the size, data type, summary, statistic, and missing values using these commands. This code. It shows here that all four columns contain 200 non-null values, so they suggest no values are missing. And it also shows that it has a float 64 data type, which means the values are numerical, and they may contain a decimals, which they have. Lastly, we checks the number of null values and adds them in each column, and we can see there are zero null values. Next, we can plot the data. Scatter plot shows the relationship between two numerical values. TV expenditure is on the horizontal axis and sales is on the vertical axis. The points show a clear upward pattern, and its growth it is positively associated. TV spending is positively associated with higher sales, and shows that it might be a strong predictor of sales. Same with radio, even though radio scatter plot is a bit more scattered, so we can infer that the relationship is positive, but it is weak. The individual relationship with sales may be weaker than the TV relation. Lastly, we check the newspaper scatter plot. From this plot, the newspaper appears to be a weak predictor, but our objective is not to use only visual judgment. We can confirm this observation using correlation, regression coefficients, and test performance. Finally, we can check for a quick overall view the pair plot and the heat map, correlation heat map. A pair plot displays pairwise relationships between all numerical variables in one figure. It provides a quick overall view of the dataset and supports the observations from the individual scatter plots. The correlation heat map the correlation heat map measures the strength and direction of a linear relationship and ranges from -1 to +1. The sales has a correlation of approximately 0.78 with TV, 0.58 with radio and 0.23 with newspaper. This also confirms that TV has the strongest individual linear relationship with sales, followed by radio, and lastly, newspaper. We also check the correlations among the input variables. Extremely high correlation between predictors can cause a problem called multicollinearity, where the individual effects become difficult to separate. The predictor correlations here are not extremely high, so serious pairwise multicollinearity is not visible. Now I will define the features and I will train the first model. So I define the input features as X and target as Y. Then I create the linear regression model and call the fit method. Fitting means the model learns that the intercept and the coefficients from the data. It chooses the values that minimize the sum of square differences between the actual and predicted sales. These differences are called errors or residuals. Squaring the errors prevents positive and negative values from cancelling and penalizes larger errors more strongly. The intercept is approximately 2.94. It is the model's predicted sales when all advertising expenditures are zero. And the first coefficient belongs to TV, is 0.0458. Holding the other variables constant, one additional TV unit of TV expenditure is associated with approximately 0.0458 additional units of sales in the dataset's measurement scale. Similarly, for radio, the coefficient is 0.1885, and for newspaper, it is 0.001. This does not prove negative 0.001, which is extremely close to zero. This does not prove that newspaper reduces sales. It means that after TV or radio are already included, newspaper adds almost no extra predictive information. And this is displayed in another pandas table. Here, I compare a few feature combinations using R-square score. Higher R-square means it is a better fit. Feature selection means deciding which input variables should remain in the model. Adding every available feature is not always useful. An unnecessary feature can increase complexity without improving predictions. In this cell, I create a list containing every useful combination of the three features. The loop trains a separate linear regression model for each combination. It stores the feature names and the R-square score and the final table, and it also displays the final table. The table also sorts from the highest R-square score to the lowest R-square score. We can observe that TV plus radio plus newspaper has the highest R-square score, while we can see that TV plus radio plus newspaper and TV and radio have almost identical scores. This again suggests that newspaper provides very little additional values. These scores use the full dataset, so they are useful for initial comparison but not sufficient for final evaluation. A separate test is required here. So the model is now trained. Now the model is trained on one part of the data and then tested on unseen data. So if the model performs well on only the training data but poorly on unseen data, it is overfitting. I divide the dataset into 80% training data and 20% testing data. The model learns from the training portion while the testing portion remains unseen until evaluation. The test size of 0.2 represents 20%. The random state is set to 42. This does not improve or depreciate the model. It makes the split reproducible, so the same observations are used for each time. After fitting the model on training data, I used predict to generate sales predictions for the test data. The first evaluation metric is R square. R square measures the proportion of variation in sales explained by the model. The value is approximately 0.8994, so the model explains about 89.94% of sales variation in this test set. The second metric is RMSE, or R root mean square error. The RMSE is approximately 1.7816, which meaning a typical error of magnitude 1.78 thousand sale units. When models are evaluated on the same test set, a higher R square and lower RMSE value are preferred. The actual versus predicted plot visually compares predictions with the correct sale values. If predictions were perfect, every point would lie on a 45-degree diagonal line with a slope of 1. Most points are reasonably close to the direction, which indicates good general performance. Points farther from the diagonal represent larger errors. Next, we also plot the residual plot. The residual is the actual value minus predicted value. A positive residual means the model predicted too low. A negative residual, it means it predicted too high. For a suitable linear model, residual should be scattered around zero without a strong curve or a funnel pattern. We can observe here most residuals are around zero, but some remaining structures suggest that the basic additive model may be missing another relationship. The histogram we were taught to use histoplots or histograms, so we also plot a residual distribution using a histogram. This plot helps us identify the skewness and the unusually large errors that may not be obvious from a single metric. Because newspaper appeared weak, I am training a simpler model using only TV and radio. The model uses the same 20% test size and the same random state, making the comparison fair. Its test R square is approximately 0.9006 and its RMSE is approximately 1.7714. I'll check again. Newspaper appeared weak. I'm training a simple model using only TV and radio. The model uses the same 20% test size and the same random state, making the comparison fair. And when I run the new model, I find out that the R square score is 0.9006 approximately and the RMSE score is 1.7714 approximately. This is slightly better than the all feature additive model. The difference is small, but when two models perform similarly, the simpler model is often preferred because it is easier to explain and maintain. This result supports removing newspaper from the basic additive model. However, the effectiveness of one advertising channel may depend on the other. For example, a customer may see a product on TV and later hear the same message on the radio. The combined effect may be stronger than simply adding two independent effects. To represent this possibility, I created an interaction feature multiplying TV expenditure by radio expenditure. The new TV underscore radio column represents their combined level. So when the interaction model uses TV, radio, and the new TV radio interaction term, I'm training a new model on that. The model uses TV, radio, and the new TV radio interaction term. Newspaper is not included because the earlier analysis showed that it provides little extra predictive value, and use the same train test fit settings, so the result remains comparable with the other models. And now I will print out the R square and the RMSE values, and voila, the R square value is 0.9742 approximately, while the RMSE is only 0.901. This model achieves a test of this is a substantial improvement over both additive models. The model explains about 97.43% of sales variation in this test, and the typical prediction error falls to about 0.90 sales units, 0.90 thousand sales units. The improvement suggests that the relationship between advertising and sales is not purely additive, TV and radio appear to work together in a way that improves prediction. This is predictive evidence of a synergy effect. It's not proof that coordinated advertising directly causes the entire increase because the data set is observational. And finally, we compare all the features, all the models. So for all features, the initial rudimentary additive model had an R-square score of 0.899, while the TV plus radio without the newspaper had a slightly better one, but our final model with the synergic effect between TV and radio had the best R-square score and the best RMSE score. We can also plot the same bar chart. We can also plot the results. The bar chart makes the R-square comparison easier to understand visually. In conclusion, TV, radio are strong predictors of sales compared to newspaper. Adding newspaper does not improve the model much. The interaction model performs the best when it includes the combined effect of TV and radio advertising. In conclusion, for the business, newspaper, the positive interaction suggests that newspaper and TV and radio campaigns should be planned together. For example, the company could use a consistent message on TV and radio during the same campaign period instead of treating them as completely separate activities. Newspapers should not necessarily be removed based on a one model. A safer strategy should be to reduce a portion of the newspaper budget and test whether reallocating that amount to coordinated TV and radio advertising improves actual sales. The company should also remember that this project uses observational data. The model identifies patterns and associations but does not prove causation. The main limitations of this project are a small dataset and the use of a single train test bed. Further improvements could include cross-validation, more observations, and other additional variables such as product price, season, region, promotions, and competition. This completes my project of sales prediction using multiple linear regression. Thank you for watching.